There are two announcements that I would like to make. The first one is about the preparation for your test 2 and cheating. I would like you to take a look on. I would like you to take a look on the discussion board. Where's my discussion? I'm sorry. I see a mosquito here. Hey, where's my discussion board? No, it's here. Announcement board, and in the announcement board number 5, two things that I will really mention. It's about for your test 2. Your test 2 will start from 5.4 conditional probability up to Poisson distribution in 6.3. Now we will finish 6.3 today. And so right after this class, you can start studying for your test 2 already. Okay, now please be aware that I will start incorporating Poisson distribution. I only started incorporating Poisson distribution in my test 2 since only last semester. So 2 semesters ago, I didn't have that in my old tests, even though I gave them my quiz. So make sure you study this part. Okay, make sure you study this part. The way I covered it is a bit different from the way our textbook covered it, but of course, you can study from both ways, from textbook and from my lecture. You will see slight difference. Our textbook actually break it into 2 parts. They distinguish mu and lambda, you will see later on, but I will just use lambda and then adjust from there. Now, as I have mentioned in my first announcement that during your test 2, you will need to have your face, your hands, and your desk visible, and your surroundings should be audible during the test. Now, please prepare all the tools you need to make it happen. So if you use computer, then you will need a webcam and microphone, or you can just use your smartphone with Zoom capability. Okay, so if you use your PC, your computer, okay, then you need to enable the webcam and microphone, and I think you need to have download the Zoom as the software. Okay, now important one. Now I found some of you cheating from each other in your test 1, and these 3 people, there are actually 3 people. These 3 people actually score very, very high in their tests. Now I recommend these 3 people to drop the class. Now I have my way to pinpoint this. I have my way to find you cheating without monitoring you online, without proctoring you directly. Okay. Now the thing is, I will only reveal to these people that I have evidence that you are cheating, even from your test 1 only. If you stay until you pass the drop deadline. Now, at that time, you cannot avoid an F. Okay? Yeah, for these 3 people, if you are getting not a high score, right? Don't worry too much about it. Okay, like for those people who get less than 70, don't worry about it. Okay? Okay, even if you're cheating from the wrong person. Okay, and then, but I don't really pay attention to those who scored quite low, below 70 in your first test. Okay, but for those who get more than 70, I found 3 of you actually from cheating. Okay, of course, I can tell who cheats from who, but when I report this to the college, I don't need to report who cheat from who. No, as long as you cheat from somebody, of course you're at fault. As long as you let somebody cheat from you, you are also equally at fault. Okay. Yeah, so please drop the class. Okay. Otherwise, if you keep staying in this class, I will make you get that F. Okay, I will make you get that F because trust me, I have my way to make it happen. Okay, been teaching for too long. No, I don't want it. Okay, I don't want it. What else? About cheating, about test two. Yes, so please pay attention to that. I need you to be able to have your webcam and microphone, or simply use your smartphone throughout the tests that I can proctor you. Okay, of course I cannot proctor you if you go to restroom, for example. Okay, so don't worry about that far. I don't need you to bring your phone to your restroom, for example. No. If you need to leave for 1 or 2 minutes, or let's say 5 minutes, because you need to scan it, from your scanner is in another room or your printer is in another room, don't worry about it. You're fine. Okay, even if you cheat, I don't think you can cheat too much in 5 minutes, right? Okay, but if you do it repeatedly, then okay, that's for the announcement for that part.
Professor, can I ask a question?
Give me a second. Somebody
Okay.
asked me this question. Can we use bathroom during test? I give you 1 bathroom time during the test, but I think in 2 hours, you don't really need it. Try to manage yourself, right? Do that before the class, before you start the test, or you hold it until you're done with the test. Okay, but if you really need to go, just go. Okay, just leave me a note through the chat. Thomas, I go to restroom, like that. Okay, yes, who asked me that question earlier?
It was me. Can I connect my phone and my laptop so that I can have one camera at my face and one at my desk?
Repeat again.
Can I have 2 devices connected to the same Zoom? So one will be with my face and the other will be with my desk, because I can't get it so that both of them are visible.
I as long as you can manage it that way, fine.
Okay, thank you.
Well, let me see. I get another. I got another. Oh, I'm sorry. I'm sorry. I'm sorry. Oops. I got an email asking me about converting to PDF. Converting to PDF is something I asked you to practice since quiz 0 and also in quiz 1, 2, 3. So please go back to that quiz 0 and see how I look at my direction. Okay. And yes, I do not want you to turn in as a picture. There's a reason why I don't want you to turn in your assignment as a picture. If you turn it in as PDF, it will take much less time compared to if you turn it in as a photo. Okay. Now, for example, if you take a photo, especially if you get a very, very good camera, then it will have some megabytes in there. Okay. Now, then for you to upload that one picture with a lot of megabytes, it will take a while. Now, imagine if you have a test, it will take half an hour. Just to upload like 4 pictures, that will be too much. Okay, that's why since the very, very beginning, I want you to learn how to do it as a PDF. Okay. What else? Yeah, that's about the PDF. The reason I want you to turn it in as a PDF. Let me go back to my note. Here's my note. I am with my note. And then lastly, about tutoring. Somebody asked me about tutoring. Where's my, okay, here. Somebody asked me about tutoring. Now, for you to get to the tutoring at our school, of course, you start with WLAC College, right? You start with WLAC College, and then you click current student. And then you scroll down, you will see tutoring here. Okay. Now then from there, there's a time though. For you to do online tutoring, it's the 9 to 5:30 Monday to Thursday, and Friday from 9 to 1. Now, one of the reason well, the good thing my class starts at 8 o'clock. So when you take the test, you have between 8 to 10, right? Okay, your test effectively 8 to 10. So you have only 1 hour overlap between the test and the online tutoring. So even if you ask tutor between 9 to 10, I don't think you will have enough time to do your test. Okay, yeah, that's my one of the concern from the math department though. From the math department, what happens if students actually consult the online tutoring during the test? Well, first, I already proctor you. Second, you have only 1 hour overlap, right? And then of course we do not allow late turn in, right? Okay. Now, that's for the tutoring in case you have questions. Now, I have one person ask me this, Thomas, I still don't understand combinations. If you cannot explain it to me, I asked you this question by email and during the lecture, but I still don't get it. What you can do is you kind of like set up an appointment with me, and then I explain it to you during my called it extra office hour. But the thing is, I remember the person who asked me that question last time asked me that question during my office hour last Friday, and that person came in like 10 minutes before I end the class. Now, of course, then I don't have enough time, right? Okay, I have another class, so I'm sorry I cannot really help you, but try to make appointment with me, okay? And then I will see how I can help. And I may be able to announce it to the whole class also if I have extra office hour. Okay, but my schedule is, let me show you my schedule. Now my schedule is, use red color. My schedule is, of course, for this class Monday to Thursday from 8 o'clock to 10 o'clock. Okay, and then I have an SMC class Monday to Friday from 11 o'clock to 2 o'clock. Now, the thing is, I am required to do once a week office hour there. So last week, I did my office hour on Friday from 10 o'clock to 11 o'clock. Okay, I was late for my office hour that day because I tried to help you. Okay, so I cannot make both of you happy. Okay, somebody yell at me there. Okay, well, I promised them that I will be online at 10, the latest 10:10. I end up going online at 10:15. Yeah, and the thing is, this week their office hour will be on Wednesday because they have a test on Wednesday. Okay, so my office hour this Wednesday at SMC, not with you, So I cannot do it with you from 10:15, from 10:10 to 11 o'clock with them. So if you need to make appointment for this week, I prefer you to make appointment with me like 4 o'clock in the afternoon, like 3 or 4 o'clock in the afternoon. So after my my class at SMC, 2 o'clock in the afternoon, right? And then give me a little rest. And then after 4 o'clock, maybe up to 9 o'clock at night, I don't give you 5 hours. No, just tell me, Thomas, which time you would like. Give me option also, okay? Either 4 to 5, 5 to 6, or 6:30 to 7:30, so on and so forth. Okay, yeah, send me an email and try to make an appointment, not like half an hour before the appointment, then you send me an email. That's not fair for me. Okay, and then later on I don't give you time. No, you don't give me enough time to actually respond to you. Okay, and I would like that to also open to the whole class, not only for one person. Okay, so I think if you want, try to send me an email later on today, right? And then let's say I will be available for office hour after 4 o'clock tomorrow, or Wednesday or Thursday, maybe even Friday, I don't mind. Okay, now your test 2 is next Monday though, next week. Okay, Your test 2 is Monday next week, but the material for your test will be done actually by today because your test 2 will only up to Poisson distribution 6.3. Okay, any questions so far? Okay, I take it as no question. Here's the thing though, I know some of you then say, Thomas, I cannot synchronously go online together with you, but then they use also, do we have, yes, that's right. We have one, actually two quizzes, quiz 8 and 9. Thank you for reminding me. The quiz 8 and 9 will be due on Wednesday. Thank you. Mikio? Thank you for reminding me. I remember your last name, Spearman. Okay, thank you for reminding me. Yes, you have quiz 8, 9 due on this Wednesday. And the first two questions you can do already, but the last question requires the lesson for today. Another question, when is your test 1? Look at your syllabus. Your test 1 is this 13th. So next week, next Monday, on July the 13th. Okay, other question? No more? Okay, I will start with 6.3, which is Poisson distribution. Now, at this point, we already learned actually two very special distribution. Maybe I write it down. So this is 6.3 on Poisson distribution. Now, at this point, we have learned two very special distribution. The first one is binomial distribution. Actually, that's the second one. We learned that through the lecture video last Thursday, and I have my office hour on Friday. I did more. Okay, but prior to that binomial distribution, we actually learned one distribution that I didn't tell you the name. I didn't tell you the name prior to that. We learned that even before binomial distribution. That distribution has a scary name. That's why I didn't tell you. The name of that distribution is hypergeometric. Hypergeometric distribution. Now, I think in our textbook, it should be in 6.4. Let me see. But at the same time, I don't think it's in our textbook. Give me a second. I mean, when I see the textbook, for example, the files I give you, chapter 6. Oh, why do I open? Give me a second. I want to confirm. Because I remember they put it in 6.4. Yeah. If you look at the first page of chapter 6, if you see the first page of chapter 6, it says 6.4 only available online, hypergeometric probability distribution. Now, with these files only, I don't think you have, with these files only, I don't think you have that hypergeometric distribution. Okay, so you depend on my lecture, or you go online to YouTube and type hypergeometric distribution. Okay. Yeah, but what is that hypergeometric distribution actually? Well, the choosing problem, the one that without repetition, the one that you cannot the same item twice. You cannot have the same item twice. Okay, so let's say, for example, we have a deck of cards, a deck of 52 cards, and then we want to select 2 cards, or let's make it 3 cards at random. Now, then if I don't say anything else, I just say select 3 cards at random, it means these 3 cards have to be 3 cards. Not selecting 1 card 3 times, no. It means at the end you need to have 3 different cards. Okay. Now sometimes I actually, or the question actually give some explicitly tell you that it is without repetition. Without repetition, which means without replacement, which means you cannot select the same card twice, which means the card that you have selected cannot be selected anymore. Okay, so either I say that with just select how many cards and that's it, it means without repetition or without replacement. Okay, now select 3 cards, then the number of ways to select 3 cards will be number of ways to select 3 cards will be 52 choose 3. Now let's say find the probability that 2 of the kings and 1 of the queen. Now notice that I don't tell you the order. Doesn't matter the order. Either 2 kings first and then queen, or queen first and then 2 kings, or the queen is in the middle. Okay, regardless the order. Notice that the event that I told you, 2 kings, 1 queen, did not imply any ordering. It's just like you get 2 kings and 1 queen. Doesn't matter which one comes first. Then that will be, let's take a look. There are 4 kings, there are 4 queens, and the rest of 44 cards, not king, not queen. Right now, then you need to select 2 from here, 1 from here, nothing from here. 3 cards, right? Okay, so your probability will be 4 combination 2 times 4 combination 1 times 44 combination 0 over 52 combination 3. Okay. Now, suppose I change the question to find the probability of getting 2 kings. Remember, we still select 3 cards, right? Okay. So when I say get 2 kings, it means the other one not king. Doesn't matter. Doesn't matter it's queen or ace or other thing, as long as not king. Now then the probability will be of 4 kings, you need 2 of them. Okay. And then of the other 48 cards, you need 1 of them over 52 combination 3. Now this is without replacement. Now suppose I change the question into this. Select 3 cards at random with replacement. Which means that whatever card you get, you put it back before you get the second card, you put it back before you get the third card. It means the same card may be selected 2 times, even 3 times. Now then, find the probability of getting 2 kings. Now, what happened is this will suddenly satisfy binomial distribution. Why? Because there will be the number of trials is 3. The probability of getting a king is 4 out of 52, which is 1 over 13. And we just need 2 kings regardless the order. And probability of getting a king in the first trial, the first draw, is the same to the probability of getting another king on the second draw and the third draw, and they're independent. So this will then becomes binomial distribution, binom PDF, number of trials 3, probability of selecting a king is 1 over 13, and you need 2 kings. Now that's the big difference between hypergeometric distribution in part A and part B, the binomial distribution. Okay. Keep in mind about can we get exactly the same cards again in the second draw or the third draw, so on and so forth. That's how we figure out if it is hypergeometric or binomial distribution. Okay. Now, Poisson distribution is a distribution which, if it shows up in your question for this class, if it shows up in your test, then it has to specifically say follows Poisson distribution notation. Let random variable x follow Poisson distribution with mean lambda. Then we denote it as x follows Poisson distribution, Poisson lambda. Okay, or in the past, they also write x follows Poisson lambda. But they never use P only, either PO, POIs, or Poisson lambda. Okay, now the thing is, again, when it is Poisson distributed, they have to tell you that explicitly. Now, when do we use Poisson distribution? Now, Poisson distribution usually being used, usually happen in situation to measure, where we measure number of incidents over a continuous domain. Now, if you read your textbook, you will see some examples on when we can use it. But most of the time, the number of incidents we are talking about is the number of arrivals. For example, number of customers over a period of time. Actually, we can also talk about number of earthquakes. over some years, or basically over a period of time also. Now, if you have heard what they call it, Southern Californian called a big one, such that in every, I think in every October we have a training, a big shake, in which we dedicate around 10-15 hours to remind ourselves what to do in case of big earthquake. Okay, now we expected to have a very big earthquake coming to us, and it's long time overdue. And the modeling, the prediction was actually done using this Poisson distribution. Okay, or number of potholes, over a certain distance. Or number of typos over some pages in our book. Okay, now of course, the way our textbook showing the work, I don't want to say it's wrong, but we will be using TI-84, right? Such that we'll use TI-84 such that the way we compute the probability in Poisson distribution will not be following our textbook anymore, because we will use calculator. Now, what is the difference between binomial, hypergeometric, and Poisson? It's double S, not single S. Okay, and Poisson distribution. Binomial and hypergeometric. Binomial, you're asking me to summarize a lecture that's supposed to be for 1 week into 10 minutes at most. Okay, binomial distribution. The number of trial is fixed. Probability of success is also constant throughout the trial, and you are interested in only the number of incidents. Okay, now hypergeometric, the number of trials is fixed. You're interested in the number of incidents only, regardless the order, but the probability changes, in which the incidence in the to get the king in the first place and to get the king the second time changes. Okay, basically that's if you have without replacement. Okay, that's for hypergeometric. Now Poisson distribution, there's no sense of number of trials, because instead of number of trials, you are given time or area or distance, something continuous. Let's say over the period of 1 hour, over the area of 9 meters square, over the distance of 3 miles. Okay, and yes, we are interested in the number of incidents only. Okay, now the thing is, then when it comes to Poisson distribution, they have to explicitly tell you that it is Poisson distribution. That's the good thing about this Poisson distribution. That's what makes it super easier. Okay, now let's go back. I will start with theoretical calculator notation. For example, let X be Poisson distributed with lambda, which is the mean, with lambda, let's say 2.3. So let's say it's 2.3 incidents on average per period of time. Okay, now then part A, find the probability that X equals to 3. Now that's the probability notation. Now then calculator notation, that will be, because we just do the number of incidents is 3, then that will be Poisson PDF. And then the first part is lambda. Okay, so this is the calculator notation. Where the first part is the n of Poisson. You will see it's either Poisson PDF or in other case later on Poisson CDF lambda, and then the second one is the number of incidents X. So in this case it will be 2.3, 3, and then you use the calculator. Okay, now copy that down first while I start my calculator. Now the calculator will be, clear this, the calculator will be, now if you remember, of course you need to practice enough this. Binomial distribution, do you remember where is that? Okay, it will be in the same category. So you go to second distribution and then you scroll down. Usually it is under binom. You see this Poisson PDF. Okay, now Poisson PDF, enter. Then they ask what's the lambda. Lambda is the average over that period of time. In this case, 2.3, that's the lambda. And the value is 3. Paste. You can see the notation here, the calculator notation. Poisson PDF 2.3, 3. Okay, 2.3 is the lambda, 3 is the number of incidents we want to find the probability on, and I get 0.20331. So from calculator, I get 0.20331. Second one, what is the probability that the number of incidents at most, let's say 3. So here I want you to contrast the difference between number of incidents equals 3 and number of incidents up to 3. Very similar to binomial case, that will be Poisson cumulative, right? CDF, Poisson CDF, 2.3, 3. Now use your calculator. Poisson CDF is the option right below Poisson PDF. You try it yourself. Poisson CDF. (2.3) and then 3. (0.79935). Hey, sorry, I forgot to share with you. 0.79935. What's the difference between Poisson PDF and CDF? I will like to ask you that question in return. Can you tell the difference between binomial PDF and binomial CDF? If you know that difference, then you know this difference. Okay, now basically, here's the thing. Basically, the number of incidents that may happen is, in binomial, it will be from 0 to n. In Poisson, is from 0 to infinity. Now, in part A, you just need the probability that 3 incidents happen. Let's say the probability that 3 customers coming in to a store in 1 hour, while part B is the probability of at most 3 customers coming through a store in 1 hour. So part B is up to 3, while for part A, that's only 3. Okay, so your question about what is the difference between PDF and CDF is exactly the same with the binomial case. Okay, it's the same to the binomial case. Is it only 3 successes or up to 3 successes? Okay, now CDF stands for cumulative density function. Use the word cumulative, that's all you need. The word cumulative. Which means up to. Okay, up to 3. And then when we use calculator, what do I get? 0.799 something. Lydia gave it to me earlier. 9935, thank you. Yes?
Quick question on the decimals and rounding.
Mm-hmm.
So I don't know if I missed it, but I know your rule is 5 decimal places.
That's right. Uh-huh.
But then you round, so you don't. What are we rounding based off of?
Yeah, then yeah, 5. We round to 5 decimal places, right?
Uh-huh.
Uh-huh.
So okay.
Yeah. When you look at your calculator, you will get 0.799347. But because you round to 5 decimal places, you need to see what's the number after that. If it is 5 or more, then you round this up.
Okay.
Okay? Yeah. When we say round, we are not truncate. Not truncate. When we do truncation up to 5 decimal places, means you just cut it off. That's truncation. No, I never say truncation. Okay, we never like just cut it off. No, we round, which means if I round to 5 decimal places, you need to know what's the number after that. You need to know what's the number on the 6 decimal place. Less than 5, you truncate. More than 5 or more, you round up.
Okay, gotcha.
Okay, yeah. So that's a regular rounding method though. Okay. Honestly, I didn't know that I have to review that, but that's my arithmetic class. 2 years before this class. Okay, now then part C. How about the probability that X is, let's say, greater or equals to 3? Now, if we try to picture the incidence that's at least 3, 0, 1, 2, 3, 4, and on. Now the incidence at least 3 refers to this, up to infinity. Now, but we don't have our calculator for that though. Then I need to get the complement first. The complement is incidence up to 2. So that is 1 minus probability that x at most 2. Then from there you use your calculator, 1 minus Poisson CDF 2.3, 2. Then you use your calculator, that would be 1 minus 0.59604. That will be 0.40396. Okay, let me show you again how to use that calculator. Where's my calculator? I turned it off. Why I have to, give me a second, something not right. Why I have so many. Let me show you how to use that calculator thing. I wonder why I turned off the calculator. Okay, binom, I'm sorry, not binom. Poisson CDF, Poisson CDF 2.3 for the lambda. The x value is 2. Enter. That's what I get. And then subtract that from 1. I would just subtract by 1 right away, but I get the opposite. So that's 0.40396. So from here, from this first example, I teach you the notation, the distribution notation. And then the calculator notation, I'm sorry, probability notation, calculator notation. Okay, now every time you use your calculator, then I need you to give me the calculator notation first for this special distribution. Binomial distribution, Poisson distribution, you need to give me the calculator notation first. Okay, and most of the time, I would like you to first write the probability notation. First write the probability notation, and then the calculator notation, and then the result. Okay, now that's for our example 1. So from this example 1, I expect you to learn only the notation and how to use calculator. Okay, probability notation, calculator notation, then how to use calculator. Now example 2, we put in 2 problems. Example 2. Let me pick question from our textbook. I have my textbook here, but it's a hard copy. That's the thing. So I need to take pictures from here. Instead of doing that, let me pick questions from our file. Give me a second. Now, I really hope that at this point you already work on your quiz, right? Which implies you have studied your binomial distribution. Okay. Now, I usually do not teach binomial distribution and Poisson distribution on the same day. The reason is they are confusing. Okay, so you need to know one thing first before you do another one. So at this point, if you don't study yet, that's usually because you don't do your homework. Or if you do, then you just cheat from somebody else. Then very likely you have a super confusing time right now. Okay, let's see this example 2. I take this from example 2 in our book. Let me make sure it's example 2 in our book. Yeah, it's example 2 in our book. It's example 2 in our book. Now let's start. A McDonald's manager knows that cars arrive at drive-thru at average rate of 2 cars per minute. So let's do that first. Let X be number of cars arriving between, I'm sorry, number of cars arriving only. And then the average lambda with average equals to 2 cars per minute. Okay, 2 cars per minute. So part A. Now, find the probability exactly 6 cars arrive between 12 noon and 12:05. So you will see that here the time is 5 minutes, right? It's from 12:00 to 12:05. That's a 5 minutes period, okay? So what is the average for 5 minutes? The lambda will be multiplied by 5, right? 2 times 5 cars in 5 minute period. Now then, probability that X equals to 6 in 5 minutes equals to Poisson PDF or CDF. We just need equal to exactly 6, right? Exactly 6. In fact, they use the word exactly, right, to help us. So that will be Poisson PDF. Okay, the average is 10. The number of incidents we want is 6. So you see I have probability notation and then calculator notation. Now then you use your calculator. Also PDF, I do it, you do it too. Make sure you know how to use your calculator though. Poisson PDF, the average is 10 in 5 minutes. The value is 6, you just need 6. 0.06306. 0.06306. Part B. Find the probability fewer than 6 cars arrive between 12 noon and 12:05. So the time is still 5 minutes. Huh? The time is still 5 minutes. So the lambda is still 10 cars per minute. I'm sorry, 10 cars per 5 minutes. Now then, what I want is probability that fewer than 6. Fewer than 6. But fewer than 6 means up to what? Up to how many cars? Up to 5. That's right. So if we try to see the possible incidents, right? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and on up to infinity. Now, when we say fewer than 6 means up to 5 only. Okay, so let me adjust that first to probability x is less than equals to 5. And then I use my calculator, Poisson calculator notation, Poisson CDF 10, that's the average in 5 minutes, up to 5 cars. Okay. When they say less than 6, you don't use Poisson CDF 10, 6, no. Less than 6 means up to 5 only. Okay, now then you use your calculator, I use my calculator too, you do it, I do it. The average in 5 minutes is 10. The number of incidents, cumulative incidents is up to 5. I get 0.06709. 0.06709. That's for part B. Part C, at least 6 cars arrive between 12 noon to 12:05. Let me emphasize that again, the time is still 5 minutes. Huh? So the lambda, the average is still 10 cars in 5 minutes on average. Now then, what is the probability that at least 6, more than equals to 6? Now, which if you think about it, that's at least 6 refers to this, right? Now we don't have calculator for that, but when we look at the complement, it will be what we have in part B, 1 minus probability that x is at most 5. That's 1 minus 0.06709. That's 0.329. I'm sorry, 93291. Now, Poisson distribution is as simple as that. Okay, Poisson distribution is as simple as that. Now, before I ask you to do some problem, let me summarize this part with this. Let X be Poisson distributed with average, the mean, equals to lambda. Our textbook use mu. Okay, then the mean expected value of X is equals to lambda. Now, the thing is the variance of this random variable X is also lambda. Poisson distribution is the only, as I know, the only distribution, at least at this point, the only distribution whose average and variance always equal. consequently, the standard deviation is the square root of that. Okay, but we don't really need that though. We don't really need this information. Maybe, but for now, I don't see that's the reason. Now, let's do some problem from our book. Let's see number 1. Let's see number 14 from our textbook. Number 14 from our textbook. Potholes on major highway in the city of Chicago occur at the rate of 3.4 per mile. So the lambda is equals to 3.4 potholes per mile. Now compute the probability that the number of potholes over 3 miles. So if the distance now, or the domain now, the distance or the time previously is now 3 miles, then I need to adjust my lambda to be 3 times that. Over 3 mile distance. So the lambda is 10.2 potholes on average over 3 mile stretch. Now I would like you to do part A, part B, part C, and of course part D also. Together with your break, we come back at let's say 4 minutes for this, 10 minutes. That's right now 9:06. We come back at 9:20. Let me start working on this. Let's see the calculator. Also PDF and 0.27. Enter. 0. 0. 0.0847. 0.08472. Part B, probability that less than 7, which means up to 6. That is Poisson CDF and 0.26.
Professor, I have a question.
Uh-huh.
So when it's equal to, we use PDF, and then when it's less than or greater than, we use CDF?
To be more precise, we use equals to, that's PDF. Less than equal to, we use CDF. Again, it's
Okay.
from the word cumulative.
Okay, thank
Yeah,
you.
cumulative. Now you did mention about less than or greater than, then use CDF, right? And I say no, not less than, greater than, but only less than, equal to, then we use CDF. Okay, let me write this down first. This is 0.11803. 803. Now what happened with part C? Probability that at least 7. Now we cannot use Poisson CDF right away from this. No, I need to do some adjustment first. See, the possible outcomes are 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to infinity. Now, what this event wants is from 7 to infinity. But our calculator cannot do that. But we can look at the complement and subtract that from 1. The probability of the complement and subtract that from 1. So this is 1 minus probability that the number of incidents, the number of potholes in this case, is less than equals to 6. And this is 1 minus Poisson CDF 10.26. That's the result we got from part B. So I just copy the answer from part B, 1 minus that. So I get 0.88197. Now, part D. Would be unusual for a randomly selected 3-mile stretch of highway in Chicago to contain more than 15 potholes. So, to say it's usual or unusual, usual if the probability of that event is greater or equals to 5%. Okay, keep this in mind. Keep that in mind. So I need to find what is the probability that x is greater equals to 15. That's equals to 1 minus probability that x is less than equals to 14. Okay. Oh, I'm sorry. It's more than 15. It's more than 15. So it should be greater than 15 here. It should be greater than 15 here. That's more than, right? Not including 15. Now the complement of more than 15 is at most 15. So this is 1 minus Poisson CDF 10.2, 15. Let's see the calculator. Zero 0.94396. 0.94396. Okay, now subtract that from 1 will give me 0.05604. This is more than 5% though, even though it's just a little bit more, but then we will still say it's usual. Okay, so should I say no, it's not unusual? Okay, the interpretation is basically the probability. Yeah, the probability. So let me pick number part C. Okay, so the probability of getting at least 7 potholes over 3-mile stretch of highway in Chicago. Is 0.881797. So approximately, if you randomly select a 3-mile stretch on any highway on Chicago, then 88 point something % of the chance you get at least 7 potholes. That's the interpretation. Okay. Now here, I guess the answer will be no. It is not unusual. The probability is actually quite small, right? But because it's not less than 5%, we don't consider that unusual. Okay, now suggested homework from here. From 6.3 will be number 7 to number, I think 7 to 17 is good enough. 7 to 17. Just do the odd ones. Okay. Now, one of another reason I mentioned this in our, that it will be in your test is because there was one semester, I think it's last semester or last year, there was one semester where the department, will it be unusual or usual if the probability is exactly 5%? It's still usual. We consider that unusual if it is less than. If it is less than 5%, so 0.04 something or less. Okay, 5% is still considered usual. Okay, but the 5% rule for usual unusual is still it's not something set in stone. Okay, so that 5% rule, that's 5% rule is commonly used. Okay, it's commonly used. If they don't say anything about the term usual or unusual, that's not something that being applied in every field. No, that's something we use. Let's say that's something we use only in social science. Okay. On the other hand, the probability that when you compute the probability you end up with exactly 5% is super small. I mean, it never happened so far. Okay, so we don't need to be afraid with that what happened with 5%, even though that's a concern though. I agree with you. I will ask that question too. But the chance that you get that 5% chance, exactly 5% chance, so far never happened. Okay, yeah, so far never happened. So don't worry about that one. On the top of that, this 5% rule, I have to mention this. This 5% rule to be the cutoff between usual or unusual. It's not set in stone. It's not something that everybody will accept in every field. What I know is when it comes to medicine, medical field, right? They use 1%. That's the cutoff. Okay. Now, most of the time, instead of saying that it's usual or unusual, they will just give the probability and let the reader or the listener make their own decision if it is usual or unusual. Okay, yeah, so the usual unusual rule of 5% is actually not standard. Okay, that's, I don't even want to say it's conventional, that's a tradition. Okay, but it's not something most people do, even statisticians. To let people decide if it is usual or unusual, they will just tell the probability and let the listener decide if it is usual or unusual. Okay. Now, let's say one thing. Okay. Let's say one thing. let's say one thing. You know that California is a majority Democrat, right? So the probability that somebody say that they vote for Republican is actually less than 50%, right? Yeah, it's not majority. Republican in California is not majority, definitely. Okay, but to say that it is unusual to find a Republican, that's also not right. Okay, because we have, for sure, we have more than 5% Republican in California. Okay, more than 5%. It's not majority, but it doesn't make it rare. Okay. The thing is, like, what I don't want to happen is you kind of like confuse between being quote unquote not majority and suddenly stretch that into something unusual. That's not true. Okay, the rules that we use for majority, the cutoff is more than 50%. The rule for unusual is 5%. Okay, of course, if it is rare, then it is not majority, right? But simply because it is not majority doesn't mean it is unusual. No, it's quite usual. Okay, now that's for this 6.3 here. Let me go on to 7.1. 7.1, properties of normal distribution. Now let me explain first normal distribution in general. 7.1, properties of normal distribution. Okay, we start with the following. We are going to learn to compute the probability of a continuous event. Okay, now in binomial distribution, hypergeometric distribution, and Poisson distribution, we dealt with discrete random variable. It tends to be the number of incidents, like number of kings, the number of tails, the number of potholes, the number of typos. Okay, and discrete random variables has the following outcomes. One of the big example is it's an integer, even though it doesn't have to be an integer. Okay, the shoe size, for example, shoe size also a discrete random variable. The size of the shoe that I wear, okay, maybe 43, maybe 42, maybe 42.5. Okay, so but we say that the random variable is discrete is you can find, if we can find two numbers, let's say 4 and 5, such that no number in between, let's say 4.7, right? Okay, if your shoe size is 4 and 5, you may have 4.5 in between, but between 4.5 and 5, there's no shoe size 4.7. Then that's how we know that that random variable is discrete. The number of siblings you have, for example, it's either 0, 1, 2, 3, 4. You cannot give me 2.7, right? Okay. You can find two outcomes. For any two outcomes, you can find a number in between that is not part of the outcomes. Let's say 2.5. You cannot tell me, Thomas, I have 2.5 siblings. That's so strange, right? Okay. Now, how about what I meant by continuous event? To be more precise, continuous random variable. Now, continuous random variable, for example, the height. I am 5 feet 10. You may be 6 foot tall, but you can easily find somebody have the height of 5 foot 11. You can easily find somebody 5 foot 11.7 inches. You can find somebody with 5 foot 11.92 inches. You can find it. I mean, if somebody tell me that his height is 5 feet 11.92 inches, I will not say that person lying. No, it is possible. Okay, it is possible. Now, so we know that that measurement, that random variable is continuous, is when any two numbers you get, any two numbers you pick, any numbers in between can also be outcomes. Then that's continuous. Okay. Now the thing is, the probability, because of this situation, then the probability of having somebody's height is exactly 510 is actually super small. Because when you ask me what's my height right now, I tell you 5'10", but when you actually measure it, it may be 5'10.2". Okay. Now, so to compute the probability of one single number of that continuous value is near zero, such that we don't actually compute it that way. We will use interval. Okay. Now, so instead of asking that, we will convert that question into the probability that, for example, the height is between 5'10" to, let's say, 5'11". Okay, then we get a better number. Okay, when I say super small here, that's basically zero. You can get somebody that you think 5'10", but when you measure it, it's either a little bit more or a little bit less. Okay, you cannot have. It's so hard to find exactly 5'10" exactly. No. Okay. Now, so instead of computing the probability of one single event, the event instead will be given in form of an interval. Okay, now let's shift to normal distribution. Normal distribution is the most frequent distribution you find in application. In fact, compare with the other three, the binomial, hypergeometric, Poisson. Normal distribution is the most commonly happen distribution in our real life. The second most common is actually binomial. The third most common is Poisson, at least the one that we use right now. Okay, so you will see normal distribution, basically one key point in statistic and probability. at which without normal distribution, there's no statistic. Now, how about normal distribution? Normal distribution let me introduce to you normal distribution curve first. Okay, normal distribution curve looks like the following. Let me see. I think I should have my second. Did I erase them? I guess I did erase them. Give me a second. Yeah, normal distribution curve looks like this. Normal distribution curve looks like that. It is it's bell shaped. So it looks like that. Let me enlarge that first. It's bell shaped. Second, it's symmetric with respect to the mean. This is the mean here. This is the mean. That's the mean. Okay. Now, when we say bell shape, it means the following: the further you are from the mean, the less likely for that event to happen. Okay. So even though the length here is the same with the length here, okay, but the probability of the event where the interval here is more likely to happen compared to the events in here, even though they have the same length of interval, but because the one here is closer to the mean, that it is more likely to happen. Okay, and like what I said before, it is quite common in our real life. Okay, because of the following. Just try to think about it. Let's say we say the mean height. I make up numbers. Okay, let's say the mean height is 5 foot 5 inches, the mean height of an adult man, let's say. Okay, then you will see that it is more likely for you to find somebody with height 5 foot to 6 compared to somebody whose height is 7 to 8 feet high, 8 foot high. So if you compare these two events here, right? Okay, both of them 1 foot interval, but because 5 to 6 is closer to the mean, then it is more likely to happen compared to the same interval length, but further from the mean. Okay, that's when we say it's bell-shaped. Now, bell-shaped also means that it is actually symmetric with respect to the mean. Okay. In other words, as much as we would like to say that somebody whose height is more than 7 foot is rare, then an adult whose height is less than 3 feet is also rare. Okay, so let's say using the illustration I have here, let's say this is 5 foot, right? Just make up numbers. I just make up numbers. Okay, let's say the mean of adult height is 5 feet. Okay, then the probability to find somebody who is 7 feet or taller is equally rare compared to less than 3 feet. Notice that I'm talking about adult. Okay, now if you include, if you want to talk about babies, of course my baby is like 2 feet length. I don't want to call that tall yet. She hardly stand up right now. But then if somebody is the average is, let's say, 3 feet, my baby is 2 feet, right? The probability of getting less than 2 feet is equally with the same probability of 4 or more. Okay, that's what it means by being symmetric. Okay, that's what it means to be being symmetric. Okay, now because of that, we will see. You know what? I want to erase that. Erase this. Erase this. Erase this. Okay. The probability of the event is equal to the probability represented by the interval, and that probability equals to the area under the curve. Okay, now we will get to that very, very soon. We will get to that very, very soon. Let me start with what we call standard normal distribution. Standard normal distribution. There are a lot of normal distributions. Zillions, a lot, infinitely many normal distribution. That's why we don't have all the tables for normal distributions. But only one standard normal distribution. Emphasize the word standard normal. Okay, now this standard normal distribution is so special that it has a special notation in our probability and statistic. The random variable being used is capital Z. Okay. Z is a random variable. Z is a random variable specially reserved for standard normal distribution. Okay, so if it is not standard normal distribution, do not use capital C. You still use X. Okay, any normal distribution, Poisson, binomial, hypergeometric, geometric, exponential, alpha, beta distribution, gamma distribution, a lot of other distributions, you use X. But once it is standard normal distribution, you use capital C. Okay, so we can say Z is a normal distribution denoted by M with mean 0 and standard variance is 1. So in general, if X is normally distributed, let X be random variable x be a normal distribution with mean mu and variance sigma squared, then the notation will be x is normally distributed with mean mu, variance sigma squared. That's the notation. Now, standard normal distribution has mean 0 and the variance is 1. Okay, now in the next 10 minutes, I will teach you how to use calculator and to compute probability of standard normal distribution only. Standard normal distribution only. Okay, so part A, let's say probability that Z is less than equals to 1.23, for example. Now, what does that mean? It means, look at the normal distribution curve. The mean for normal distribution is 0. Okay, now 1.23 is located to the right of that. Let's say it's here, 1.23. Now the event Z less than equals to 1.23 refers to this interval. From negative infinity up to 1.23. Now, the probability of this event, is equal to the area on that interval, the area under the curve of that interval. So you will see the area under this curve in total is 1. And of course, the area here will be less than 1. Now, what is the calculator notation? This will be normal CDF from negative infinity up to 1.23, followed by the mean and standard deviation. The calculator notation will be normal CDF, lower fence, in this case negative infinity, upper fence, the mean and the standard deviation. Now, the thing is, we don't have negative infinity on our calculator. So we will replace that with negative E99. Oh, what is that, Thomas? Now let's take a look on our calculator. Let's take a look on our calculator. Okay. Just like other distribution, normal CDF is located under the category of normal or of the distribution. The second option, we have normal CDF. Okay. Now, the lower here, the lower fence is negative infinity, right? You can use a super small number, let's say negative 1 million if you like. You can do it that way, okay? You can do it that way. Now, but if you want negative infinity, negative E99, for example, the negative you use cannot use subtraction sign. No, do not use subtraction sign. The negative you use will be this sign here. Negative. Now, how about E99? It refers to it refers to this E99 here refers to the scientific notation -1 times 10 to the 99. Yeah, so this 99 here refers to 10 to the 99. Now then, how do we type it on calculator? I already have the negative now, right? I have the negative now. And then how to get the E? The E is actually the one above the second of that comma. Not this E, not this E. Not a natural number E. No. Not this natural number E. No. I'm talking about this. On your calculator, it is written as EE, but when you type it, you will see capital E. Okay? 99. Enter. The upper fence is 1.23. The mu is 0. The sigma is 1 pace. And you will see the coding there. Enter. So I get 0.89065. That's 0.89065. Okay, again, because we don't have negative infinity on our calculator, we will replace this notation here by negative E99. Okay, so let's say, for example, again, I ask, what is the probability that C is less than negative 2.14? Okay, let's sketch that first. This is the mean 0. Negative 2.14, of course, to the left of that, right? Now you need the Z to be less than that. So the event, as we can see here, is less than half of the curve, right? So the probability is definitely less than 50%. Okay, now how about the calculator notation? Calculator notation will be normal CDF, negative infinity, which we replace by negative E99, up to negative 2.14. The mean is 0, the standard deviation is 1. Notice that the standard deviation is, the variance is 1, therefore the standard deviation is also 1. Now then you use your calculator, normal CDF, negative E99, enter, negative 2.14. The mean is 0, standard deviation is 1, compute it. I get 0.01618. Let's do more. How about the probability? The probability that C is actually greater than, C greater equals to, let's say, 1.94. So let's picture that first. The mean is 0, 1.94 is to the right of that, of course. And then we need the area under the curve on that interval. Then the interval will be, oops, it will be normal CDF, the left fence. Now, oh, by the way, the notation that we use here, the notation we use here, before the mean and variance, this notation here actually follows interval notation in your algebra 2. Now, if you remember how we wrote our usual interval, we write it using interval notation. That's basically it. So the interval notation here is from 1.94, actually, because I include the endpoints, I use bracket. But when we use calculator for this continuous distribution, using bracket or parentheses doesn't make a difference. That's the notation, right? From 1.94 up to infinity. Now, then you mimic this left hand 1.94, and the right fence is infinity, which is E99. Okay, then I use my calculator. Normal CDF 1.94. That's the left fence, lower fence. And then the right hand side, the right fence is infinity. So I will use E99 right away to represent infinity. Enter, the mean is 0, the standard deviation is 1. I get 0.02619. Check. Plus 1.
Professor,
Yes,
the 194 is in the lower fence because it's less than Z?
yes, to be more precise, C is greater than.
Okay.
Greater equals to, right? So we want the interval where the C is from 1.94 and higher. Now, I strongly suggest you to, instead of just reading it from here, sketch that first. Sketch that first. Okay? Yeah. You see that when it comes to this kind of things, I strongly suggest to sketch it because notice that a lot of you, well, a lot of you actually like to tell me, not in this class though, in my algebra class, in my pre-calculus class, my calculus classes, I have students keep on telling me that they are a visual person, right? And I think you are too. Thomas, I'm an audio-visual person, right? But the thing is, when it comes to this question, strangely, not a lot of people want to graph it, even though they are a visual person. Okay, so I strongly recommend you to use what you call your strong point. You're a visual person, right? You want to see, then why don't you draw it yourself? Okay, yeah, so my recommendation is draw it. Now, by the way, this statement is not directed to the person who asked me that question earlier. No, I'm just telling you that the best way to answer this question is by try to figure what the graph look like first. Okay, because I can say when it comes to wording, there are actually a lot of ways to word this. C is at least 1.94. Now, reading it as 1.94 is less than equals to C may not get your mind in place until I read my Z is greater or equals to 1.94. That's just two different ways to say it. When I say I'm older than you, it's the same to say that you are younger than me. But one of them is okay, the other one may be a bit offensive. Okay. Imagine if I meet a lady. Now it doesn't. Well, I happen to use yellow, but it doesn't have to be yellow. Okay. Don't get into political. No, that's not my point. Okay. When I see a lady, I don't think it's polite to say that you're older than me. At least in my culture. Okay. To say that that lady is older than me sound a bit offensive for that lady. But when I say I'm younger than that lady, sound humble. You see what I mean? I'm younger, and therefore I listen to her more. Okay, but to use the word old for a lady, nah, avoid that. Even though those two statements are actually the same statement though. I'm younger than you, you're older than me, they're actually the same statement, right? Okay, but one of them being perceived as something a bit offensive, another one is perceived as a sign of humbleness, right? Okay, now I hope you understand what I meant by that. Okay, so maybe when we say it another way, it's better for us. I know I'm over time, but let's do one more example. This time, if I want to find the probability that Z is between negative 0.2 to 0.7, can you type that down first? Does it matter where the sign less than inclusive or exclusive? Whether it is with equal sign or without equal sign? For continuous distribution, with or without equal sign doesn't make a difference. In other words, even if I put equal sign here and equal sign here, it will not change that, because remember the probability that Z is exactly negative 0.2 is basically 0. It's continuous, right? Remember my illustration about the height, right? The height for exactly that one number is super small, it's basically 0. Okay, such that using the same perspective here, to get exactly negative 0.2 is basically 0. Therefore, either you include it or you don't include the endpoints, that will still be the same for continuous distribution. For discrete, it makes a difference. Okay? For discrete, it makes a difference, but for continuous, it will be the same. Now, calculator notation will be normal CDF negative 0.2, that's the left fence, right? Maybe we draw it first. Negative, this is 0, negative 0.2 is here, 0.7 is here. So this is the interval we look for, right? And this is the probability. The probability is represented by the area under the curve in that interval. Okay, so the left fence is negative 0.2, the upper fence is 0.7, the mean is 0, standard deviation is 1. Negative 0.2, positive 0.7, the mean is 0, standard deviation is 1, boom, boom, boom. 0.0330, huh? 0.33730. Check. Yeah, because the after that 9 is 6, right? So I round it up. Okay, now this is where I will stop today. Tomorrow I will go on with 7.2. This is basically what you need to learn from 7.1. It's just how to use the calculator, what it means to be normal distribution. Okay, and tomorrow I will do 7.2, which cover a bit of 7.1, and after that I will go on with I may go on with chapter 8. Okay, but I will focus more on 7.2 tomorrow. Okay, see you then tomorrow.